Last week we took a look at, among other things, we took a look at 3 of Kepler's laws. Remember Kepler, excuse me, the latter part of the 16th century, came up with 3 laws that describe the motion of the planets around the sun. The first one we call the Law of Elliptical Orbits. The Law of Elliptical Orbits, as you might remember, said the sun is somewhere, and then all planets, including the Earth, revolve around the sun with the sun at one of the focal points of that ellipse. So in other words, if there's the sun, the Earth has to revolve around the sun either like this, with the sun at the left focal point of that ellipse, or the Earth has to revolve around the sun like this, with the sun at the right focal point. Doesn't really matter. Okay, it doesn't really matter which is which. Some planets would have it at one focal point, some planets would have it at the other focal point. Doesn't make any difference. Okay, every planet has to revolve around the sun, and in an elliptical path, although not quite as elliptical usually as we have it drawn there, with the sun at one of the 2 focal points. Now, the second law, this is the one that, to be honest, I think is a little bit confusing. This was the law of equal areas. Remember, this one said a line that joins the planet to the sun sweeps out equal areas in equal time intervals. What did that really mean? Well, if we had the sun drawn over here, with the Earth revolving around the sun like this, notice the sun is still at one of the focal points there. Here's the Earth. Here's a line joining the Earth to the sun. Fast forward a little bit later, maybe a few days, maybe a few weeks, whatever. Okay, whatever time interval we'll call T1, it's going to sweep out an area in here that we're going to call A1. Now, later on in the year, maybe 6 months later, the Earth is way over here. Fast forward another little bit in time. We'll call it T2. The Earth is right here. We join the Earth to the sun again. During that amount of time, it sweeps out an area that we call A2. Now, if T1 equals T2, in other words, the time interval there is the same, then the area that's swept out is going to be the same as well. And that has an implication in terms of the speed of the Earth and other planets, for that matter, as it goes around the sun. What happens to the speed of the Earth as it goes around the sun? Yep. Yeah, it changes speed, and it speeds up as it's closer to the sun. And the closer the Earth is to the sun, the faster it goes, and that goes for other planets as well. Now, because of the elongated ellipse that I have drawn here, the exaggerated ellipse that I have drawn here, the effect would be much greater in this picture than it really is. There is a change of speed as the Earth gets closer to the sun. It's just not nearly as dramatic as we have it shown in this diagram. Okay, it's measurable, but it's not huge. All right, the third one we called the law of periods. The law of periods basically said that, look, the square of the period of revolution of a planet around the sun is proportional to the cube of the radius of revolution of the planet around the sun. So in other words, a constant, k, we called it, is equal to t squared over r cubed. Now, the constant k for the sun may be equal to t squared over r cubed using data for the Earth revolving around the sun, or it might be for Mars going around the sun, or it might be for Jupiter going around the sun. It doesn't really matter. As long as we're dealing with data for an object revolving around the sun, t squared over r cubed will be the same. Okay? Ks for the sun will be the same as Ks for the sun, will be the same as Ks for the sun, whether they're using data for the Earth, Mars, or Jupiter. That's helpful to us because it allows us, given data for one planet, to solve for data for another planet. Now, having said that, we could say that the Earth has a Kepler's constant as well. That could also be equal to t squared over r cubed. But it's not going to be t Earth over r Earth squared or t Jupiter over r Jupiter squared. It might be the period of the moon squared over the radius of revolution of the moon cubed. Or it might be t of the International Space Station squared over r of the International Space Station cubed. So KE will be the same as KE. It'll be different than KS. We can solve for KE or KS using data for anything revolving around that object, KE or KS. All right? Make sense? Next, we talked about why this happens. Okay, we talked earlier in the week about how it happens, right? There's Aristotle, there's Copernicus, there's Tycho Brahe, there's Johann Kepler. This is how it happens. But why does it happen? That's the last thing we did last week. That was Newton and his law of gravitation. We said that every two objects exert a gravitational force on each other. Every two objects with mass exert a force of gravity on each other. So the apple and the earth exert a force of gravity on each other. The apple falls, the earth doesn't rise because the apple's a lot lighter, but it's the same force. The earth and the moon exert a force of gravity on each other. The moon is affected more by that because it's lighter. You and the earth exert a force of gravity on each other. Again, it affects the you more because you're a lot lighter than the earth is. You and your neighbor exert a force of gravity on each other. It's such a small force because your mass and your neighbor's mass is so small as well. There is a force of gravity between every two objects with mass, and that force of gravity is equal to G, m1, m2 over r squared. G being a constant that we call the gravitational constant, 6.67 times 10 to the minus 11. If we're talking about the moon and the earth, m1 and m2, which one is which? Which one is m1, which one is m2? The moon or the earth? Doesn't matter. Doesn't matter. 1 times 2 is 2. 2 times 1 is 2. It doesn't matter what order we multiply numbers in, so it doesn't matter which one we make m1, which one we make m2. R stands for what? R stands for what? Fraser's your hand up there? Yeah, it's the distance that separates the centers of the two objects. Good. Now, we see this often and we think automatically that it stands for a radius, right? The radius of orbit of the Earth around the sun or whatever. And it can, but not necessarily. Okay, it's from the center of one object to the center of the other. Now, if one's going in a circle, then that distance will be the radius. But we don't have to be moving in a circle to still solve the problem. No, we don't have to be moving at all, exactly. What units would we measure R in? What units is R going to be measured in, Daniel? Meters, good. What units is F going to be measured in? The force. Newtons. It's a force, right? Force of gravity can also be known as what? It's a one-word answer here. Starts with a W. Force of gravity is the same thing as... Force of gravity is the same thing as... You guys know this. Wait a second. Give yourself a chance to think about this. Just wait. Just wait. Force of gravity is the same thing as what? Bo? Yes, good. Weight. Force of gravity is the same thing as weight. So clearly, if you're asked a question where it says find the force of gravity, then this is what you can do. But if you're asked for weight, you can also do this. Now, we learned much, much earlier in the year that the force of gravity is also m times g. Why can we not always use this equation? Why do we have to go to this more complicated equation from this one? This one seemed a lot simpler to find force of gravity. Fraser? You're right. The force of gravity isn't constant, but why isn't it constant? Josh? Yeah, gravity itself isn't constant. On the surface of the Earth, it's still safe to assume that little g is 9.81 meters per second squared, although that does change a little bit depending upon where you are. But if you go up higher, to the top of a astronomically high skyscraper or the top of a mountain, or you go to space, then g isn't 9.81 anymore. G is some other value. Maybe we're not even trying to find the force of gravity between you and the Earth. Maybe it's between you and the International Space Station or whatever, yeah. So we can't always assume that g is 9.81. When we can, this still works just fine. When we can't, then we've got to go to this equation. Make sense? All right. We did a sample problem with this on Friday, but we're going to do another quick one right now. You don't have to copy this one down if you don't want, but you can if you want as well. We're just going to say, guys, that you got a person who's 75 kilograms. A 75 kilogram person is in the International Space Station 400 kilometers above the Earth's surface. We want to find that person's weight. In other words, we want to find the force of gravity that acts on that person. The force of gravity that acts on that person is g m1 m2 over r squared. It's actually m times little g still, but we don't know what little g is. 400 kilometers above the Earth, little g isn't 9.81 anymore. Okay, it's not zero, as a lot of us think that it is. There's still gravity. There's still a lot of gravity in the space station, actually. The only reason that the astronauts appear to be weightless and float around is because they're falling. They're free falling. It's a constant free fall as they orbit around the Earth. But it's still lower. Okay, it's not zero, but it's still lower than what it would be on Earth. We're not going to use m times g because we don't know what little g is. We're going to use g m1 m2 over r squared. G we know is 6.67 times 10 to the minus 11. M1, let's use the mass of the person, 75. M2 is going to be the mass of the Earth. That's on your data sheet, by the way, if you don't remember what it is, which we used it once on Friday, but you're probably not going to remember that. Check your data sheet. It's 5.97 times 10 to the 24 kilograms. What do you think R is going to be? 400? 400,000? Which one is it?
Would it be 400 plus the radius of the Earth?
Yeah, it's actually 400,000 plus the radius of the Earth. You check on your data sheet right now. Flip it over. You're going to see a whole bunch of things, including the average radius of the Earth, which is about halfway down. 6.37 times 10 to the 6 meters. We're going to use that number, 6.37 times 10 to the 6 meters, plus 400,000. And we can't forget to square that because it's gm1 m2 over r squared. Let's do this on our calculator now. See what we get here. I think so, but we'll do it on the calculator to make sure. Let's go 6.67 times 10 to the negative 11 times 75 times 5.97 times 10 to the 24. Let's press equals, and then let's divide that by, be careful to use some brackets here, okay? We want that entire bottom number squared, not just the last number squared. So use some brackets. Let's say 6.37 times 10 to the 6 plus 400,000. Let's end those brackets, and then let's square everything inside those brackets. Should give us our answer. We get 651.6 newtons. That's going to be 6.5 times 10 to the 2 newtons. So that's the person's weight on the International Space Station. They appear to be weightless. But remember, we said they only appear to be weightless because they're free-falling. They're not weightless. But they weigh less than they would on Earth. Just out of curiosity, now, we're not asked in this question to do this, but just out of curiosity, I wonder what the weight of the person would be on Earth. We can figure that out without using this big new equation. We can just say m times g for the weight on Earth. 75 times 9.81. What do we get for that? 735, 7.4 times 10 to the 2 newtons. So the weight has gone dramatically down because we're 400 kilometers above the Earth. If we had assumed 9.81 meters per second squared for the acceleration due to gravity on the ISS, then we would have gotten the wrong answer. You can see that it works on Earth, but it doesn't work when we're not on Earth, when we're off the Earth a significant distance. All right? Is that good? All right, then. See what you can do with those two. All right, everyone, you've had a chance to work on those. Any questions with page 1 or page 207, number 1 and 2? Number 1? Number 2, all right. 1 and 2 it is. 1 says two people, A and B, are sitting on a bench 0.6 meters apart. A has a mass of 55, B has a mass of 80. What's the force of gravity of B on A? Let's say R is 0.60 meters because that's our distance that separates them. We're going to say M1 is 55 kilograms, and M2 is 80 kilograms. Does it matter which one I call which? If you went the other way around, does it matter? Not at all. We want to find the force of gravity of B on A. So let's say F is equal to G M1 M2 over R squared. That's 6.67 times 10 to the minus 11 times 55 times 80 over 0.60 meters squared. Now, which force am I finding? We were asked to find the force of B on A. Am I finding B on A right now, or am I finding A on B? We know the answer to this question. Okay, B on A or A on B? Or is this some kind of trick question? And what's the answer? Aiden, is it B on A or A on B? Same thing. It doesn't matter. We're looking for the magnitude, right? We know the force is going to be opposite in direction, equal in magnitude. We're only looking for the magnitude, so it's going to be the exact same answer there. Okay, when we do the math here, we should get 8.2 times 10 to the minus 7 newtons. Can you tell me, please, why I got such a small number for that force of gravity? Why did I get such a small number for that force of gravity between person A and B? We're dealing with people here, right? The mass of people is very, very small. When we're dealing with the Earth, the force of gravity is a lot bigger. Okay, let's take a look at number 2 now. It says the mass of the Titanic was 4.6 times 10 to the 7 kilograms. Suppose the magnitude of the gravitational force exerted by the Titanic on the fatal iceberg was 61 newtons. That's actually a big force. 61 newtons is a very, very measurable force. Why do you think, though, with such a big force, 61 newtons, that the Titanic wasn't literally pulled toward the iceberg? It hit it, it drove towards it, but it wasn't pulled towards it. Why would 61 newtons not pull the Titanic towards it? Yeah. So a force of 61 newtons on a little bug would do a lot. A force of 61 newtons on the Titanic wouldn't even be felt. So it's a fairly big force still, measurable force, but it's just a force that wouldn't do anything to something that was that massive. All right, let's say F is equal to G M1 M2 over R squared. Now, we're looking for either M1 or M2. Let's say here M2. Let's take the R up by multiplying. Becomes F times R squared. Now we want to find M2, so let's take G and M1 over to the other side by, what are we going to do with this? Dividing, right? Becomes F times R squared over G times M1. The force of gravity here, 4.6, is 61 newtons. The distance, I think they said, was 100 meters. Yeah. Can't forget to square that. 6.67 times 10 to the minus 11 times M1, which was 4.6 times 10 to the 7. Let's do this one on our calculator as well to make sure that we can do this. Okay, follow along with me, please, on this one. Let's say 61 times 100 squared. Let's divide that by, and let's use some brackets on the bottom because we want to multiply both numbers, okay, inside the brackets. 6.67 times 10 to the minus 11 times 4.6 times 10 to the 7. Do that math. We get 1980. Oh, I don't like it when we get numbers like this. 190. We got to convert that to scientific notation, right? I mean, in the end, we could go 1.99. We're going to round it to how many digits? Round it to 2 digits. Yeah, 2 digits, so it's going to be 2.0 times 10 to the something. We can count decimal places, but sometimes some of us have a little trouble with that. Okay, we mess up on the counting, or we move it the wrong way, make it negative when it should be positive, or so on. I'll show you a little trick here, okay? If we get that answer, and we want it in scientific notation because we've got to make it 2 digits, and we don't really like converting it to scientific notation, then go back into your calculator and do this. Go mode, scientific notation, and then let's multiply that answer by 1. Multiply it by 1, we're going to get the same thing, right? Except now, it's going to be in scientific notation. So that's going to be 2.0 times 10 to the, tells us right there, it's 10 to the 8. Yep.
If our calculators use E to represent times 10 to whatever,
Yep.
why don't we use that in normalization?
I don't know. I wouldn't mark it wrong if you did, though, Rucker. Is that good? Chase, is that okay? Was it the rearranging there that was the issue? Or? Okay. Let's take a look at another question now. Shift gears just a little bit. It's still on Newton's law of gravitation, but it is a problem involving something that we call variable value changing. We did 1 or 2 of these earlier in the year, but not very much of it at all. This one says object A exerts a force of this value on object B. We want to find out what the magnitude of the force becomes if we double the distance. We increase the mass of object A by a factor of 6, and we cut object B's mass in half. We want to find the value of the force here. Now, we're trying to find what happens to a variable here without knowing what the values of the other variables are. What does the force become when we double something that we don't even know what it was? When we increase something by a factor of 6 when we don't even know what it was to start with? And variable value changing is what I want to do for this. We're going to start off by saying my equation, my relevant equation, is gm1m2 over r squared. You always want to pick that relevant equation. That equation that you would use to solve the problem if you knew what the numbers were to begin with. Okay, so it shouldn't be hard so far. Right? It's no harder than the problems you just worked on, for sure. At least not so far. We're going to make that relevant equation equal to our original value. We'll call it FO, my original force. This is what my force is when I start the question, gm1m2 over r squared. And we'll also set that equal to 1.3 times 10 to the negative 10 newtons. So nothing groundbreaking yet. All I've done right now is basically written down what the question tells me. We're told that the force of gravity is 1.3 times 10 to the negative 10 when I start this question. We know that it's also equal to gm1m2 over r squared because that's what appears on my data sheet. Let's go from there. Let's say now my new force. My old force was 1.3 and gm1m2 over r squared. My new force is now g times 6m1 times 1/2 m2. Listen carefully to the next sentence that I'm about to say here. I've always told you that the force of gravity is equal to this equation. The force of gravity is equal to gm1m2 over r squared. That's not quite true. F is not equal to m times a. V is not equal to d over t. A is not equal to delta v over delta t. Those are representations of the equation. V is equal to the displacement over the time. And the displacement we usually call delta D, but in England, they usually call it S for whatever reason. Okay. Maybe it's separation. I'm not sure why they call it that. It doesn't matter what we call the distance. Okay, velocity is distance over time. Whether we call it S over T or whether we call it D over T, it doesn't make any difference. Okay. The force of gravity is the constant times the mass divided by the distance squared. It doesn't matter whether we call it gm1m2 over r squared or we call it something else. It's still the same equation. This is just a representation of the equation. So the force is still going to be the constant times the mass over the distance squared, but the mass is no longer m. We just called it m before. Now we're not going to call it m anymore. If it was m, now it's 6m. If it was m2, now it's 1/2 of m2, because we've changed its value. Does that make sense? This is just as valid. Force of gravity can still be this. We're just representing the mass by a different variable now. It's not m, it's 6m, or 1/2 m. Now r is doubled, it says. The distance is doubled, so we're going to make this 2r. Make sure you square everything inside those brackets, because we're not doubling, or we're not squaring r, we're squaring the distance. And the distance is not r, the distance is 2r. Got to square everything there. Here's a question for you. What's 1 times 2 times 3? There's a brutal, tough question for us. 1 times 2 times 3. What's the answer to that question? 1 times 2 times 3, Krista? Good, 6. What's 2? Here's a even tougher one. What's 2 times 1 times 3? Alex, 2 times 1 times 3. Good. What's 3 times 2 times 1? Doesn't matter what order we multiply them in, it's 6. So if 1 times 2 times 3, 2 times 1 times 3 are the same thing, then g times 6 times m is the same as 6 times g times m, right? Let's pull these numbers out in front. 6 times 1/2 times g m1 m2. Is that the same thing as we had on the top over there? Doesn't matter what order we multiply them in. So g times 6 times m times 1/2 is the same as 6 times 1/2 times g times m. Now, let's pull that 2 out in front as well, but it's squared, so let's make it a 4. Six times 1/2 divided by 4. All we're doing here is pulling the numbers out in front, just because it's neater that way. 6 times 1/2 is 3, divided by 4. Okay, 3/4 g m1 m2 over r squared. Now, here's the crux of it, right here. We know the value of g m1 m2 over r squared. Right? It's the first thing we wrote down. It's 1.3 times 10 to the negative 10 newtons. So what we're going to do here now at this point is say it's 3/4 times 1.3 times 10 to the negative 10 newtons. We replace gm1 m2 over r squared with what we know it to be, because that's what it told us in the question. We take 3/4 of that, which isn't very hard to do. Say 1.3 times 10 to the negative 10, times it by 3, divide it by 4, gives me 9.8 times 10 to the minus 11. Did you guys follow that? I'm not usually a huge fan of math, but sometimes it's kind of elegant in what it can do, right? This is a mathematical exercise. It's related to physics, but it's really a mathematical exercise. Okay, we don't know what the value of any of these variables are, but yet we can figure out what the new force becomes just by how much the other variables have changed, not by what they are, but what they've changed by, just by using a little bit of a mathematical trick. Yep. Why do you say that? Is it hard? Okay, well, that's what I was asking. Did it make sense, right? You didn't. You might have said no to yourself, but not out loud. Next time you got to say it out loud. Okay. Let's just real quickly go through the steps again. Okay. Step number 1. Okay. Step number 1, guys, has got to be easy for us. Okay? I'm not suggesting the rest of it is easy. If you had trouble with the rest of it, that's fine. Okay. But step number 1 has got to be easy. Right? The question says what is the force? What is the gravitational force? If we had numbers for M and R, this is the way we'd do it. F is equal to gm1m2 over r squared. So write that equation down. We know its value. We're told its value is 1.3 times 10 to the negative 10. So write that down. Write down what we're told. Here's the equation. Here's the value. Done. Step number 1. Now, step number 2 is where it becomes a little bit trickier. Step number 2 is, what is my new force? My original force, FO, is this. My new force, Fn, is, well, it's the same equation, but look at the changes I've made here. Let's try a new color here. Let's go with purple. How about this one? Is that kind of purplish? It's not M anymore. We increased M by a factor of 6, so it's 6M. Just put the number in there. A half M. Just put the number in there. 2R. We doubled the distance. Just put the number in there. Then, when we have those numbers added to it, to this step number 2, then we're going to go to step number 3, which is pull those numbers out in front. The 6, the half, and the 4 out in front. Why can I do that? Because it doesn't matter, Travis, what order I multiply numbers in, as long as I multiply the same numbers. Here we said, in the little thing that we did before we answered this, we said 1 times 2 times 3 was 6. 2 times 1 times 3 was 6. 3 times 1 times 2 was 6. Okay, if I was multiplying 1 times 2 times 3, and for whatever reason, let's call it x is equal to 1 times 2 times 3. If for whatever reason I wanted to pull the 3 out in front, would that be okay? Is that the same thing? Yes? All right, so if I had x is equal to g times 6 times m, would it be okay to pull out the 6? Would that be okay? If g is a number and m is a number, and I can pull out the 3 in the example that we had at the top, then there's no reason why I can't pull out the 6 there, right? G times 6 times m is the same as 6 times g times m. Now, I've only done the exact same thing with the half as well. It gets a little bit more complicated here because there's 2 numbers that I'm pulling out in front and 3 other variables. But I'm just doing the exact same thing. I'm just changing the order that I'm multiplying these numbers in for convenience. I don't even have to do that. It's just convenient to do that so that when I get to this step down here, it becomes a little bit easier. Okay, does that make a little bit more sense? Okay, so we pull those numbers out in front. This bottom one is pretty tricky, though. It becomes a 4, right? Why does it become a 4? Well, if it's 2 inside the brackets, and the brackets are squared, then it's got to come out by squaring it. 2 times 2, 2 squared is 4. The 4 comes out in front there. So I get 6 times a half over 4, which is the same as 3/4, times whatever I got left here, gm1m2 over r squared. And how do we know to plug in the value of 1.3 for that? Because that's the first thing we wrote down. gm1m2 over r squared is 1.3. Okay, that's what the question told us. Does that make a little bit more sense? Okay. Travis, the question you asked when I started going over that again the second time was, is this going to be on the test? This kind of question is actually more of a physics 30 question, to be honest with you. Okay. I probably wouldn't put one of these on a test. I might put one on a quiz just to see where you're at with it, but I probably would not put one on a test. Okay, that doesn't mean that we shouldn't do it, and it doesn't mean that you shouldn't try to know it. Okay? Sometimes we do things just to get your mind going a little bit, to expand it a little bit. And okay, it sets the stage a little bit more for Physics 30 next year, where you have to do this a lot, actually. Okay with this? Step 1, step 2, step 3, and really the last step, step 4, is subbing in that number, solving. See what you can do with these 2 questions, please. Let's take a look at question number 1 here. It says, object A exerts a gravitational force of magnitude 5.9 times 10 to the minus 11 newtons. That's a force. I had a couple of people ask me, is that F or is that G? G is never 5.9. It's always 6.67 times 10 to the minus 11. It's a constant, and it will never change. no matter where you are in the universe. We call it a universal constant because it always stays the same no matter where you are in the universe. It's universal. That's F. So we know what the value of F is. We want to know what happens to that F. This is what I start with, right? My original force. What does F become? What's my new force after I make changes to it? After I increase the separation distance, I increase mass and decrease mass, what does it become? Let's say F original is equal to G m1 m2 over r squared. This is the equation that I'm always going to use for these problems. Right? That's what my force is, G m1 m2 over r squared, but it's also equal to 5.9 times 10 to the minus 11. That's before I make any changes to it. I'm going to make changes to it. I'm going to increase my distance to 4/3 of what it was, and I'm going to cut one of my masses in half and so on. I'm going to make changes to it, but before I make those changes, this is what it is, my original force. Now, my new force is still equal to G times my mass divided by my distance squared, but we're no longer going to call it mass m. We're going to call it 3/2 m. I've changed the first mass to 3/2 of what it was before. So I'm not going to call it m. I'm going to call it 3/2 m. The second mass is half of what it was before. So I'm not going to call it m2. I'm going to call it half of m2. And my distance, which was represented by r, is now 4/3 of what it was. So instead of being r squared, it's going to be 4/3 r squared. And you got to remember to put that 4/3 inside a set of brackets. This is what my new force is. This is what my force becomes after I make changes to it. Now I want to simplify this. I don't have to, but it makes it a lot easier down the road if I do. Let's simplify this by pulling those numbers that I just put into it out front. The 3/2 comes out in front. The 1/2 comes out in front. So on the top, I've got 3/2 times 1/2 times gm1 m2. That's exactly the same thing as what I had in the last step. I've just changed the order of the numbers, that's all. If 1 times 2 times 3 is the same as 2 times 1 times 3, then this step is the same as this step. Now, 4/3 has got to be squared to pull that number out in front as well, because it's inside the brackets. 4/3 squared is 16 over 9. 4 squared, 3 squared, 16 over 9. And then, of course, we've got to square the r as well. And this looks a little bit ugly, but we can simplify this. 3/2 times 1/2 is going to be 3/4. Right? 3 times 1, 2 times 2 is 3/4. Divided by 16 over 9. And look, we know the value of gm1 m2 over r squared. The first thing we wrote down. So let's just sub that in now. Now, we can simplify this a little bit further if we want to, or we can just plug in the numbers as we have them in our calculator. 3/4 divided by 16 over 9 is the same as 3/4 times 9 over 16. We divide by a fraction, we multiply by the reciprocal, or we can plug the numbers into our calculator using brackets, get the same thing. Multiply those numbers together, we end up getting 2.5 times 10 to the minus 11 newtons. So again, our steps. Step 1, the easy one. Write down the equation and write down what it's equal to. This is what we start off as. Step number 2, make your changes. Instead of being m1 m2 over r squared, it's now 3/2 m1 times 1/2 m2, so on. Make your changes. Step 3, let's pull the numbers out. Let's just change the order in which we're multiplying it here. Get the numbers out in front, just because it's easier. And then step 4 is sub in my original value there. 5.9 times 10 to the minus 11 newtons. And then just plug your numbers into your calculator at that point and get your answer. All right? Let's real quickly go through B as well, and then I'll give you one more question on this, and then we'll move on. move on with this, okay? Question B says, look, my force was GM1 M2 over R squared, but it was also equal to, we were told in the top of the question here, 5.9 times 10 to the minus 11 newtons. This is what it was. The exact first step, exact same first step as I had in question A. Because that was in the first part of the question, the stem of the question. It said, here's the value of the force. Now I make my changes to it. This is my original force. My new force is now G times, what are we doing here? MA is cut in half. So it's going to be 1/2 M1. M2 is 5/4 of what it was before, 5/4 M2. And R is decreased to 1/6, so R is not going to be, or the distance isn't going to be R anymore. It's going to be 1/6 of R. Okay, this is step 1. This is step 2. Okay, write down the equation, then make your changes. Step 3, we want to pull those numbers out in front. We're going to say Fn is equal to 1/2 times 5/4. No reason why I can't pull them out in front. Times G M1 M2 over 1/6 squared is 1/36 R squared. Now look, we know the value of GM1 M2 over R squared. It's 5.9. We could simplify this a little bit as well in step 4. 1/2 times 5/4 is 5 over 8 over 1 over 36. Multiply that by 5.9 times 10 to the minus 11. Same thing as saying if we want 5 over 8 times 36 over 1, or we can just plug the numbers into our calculator. When we do that either way, we end up getting 1.3 times 10 to the minus 9. 1.3 times 10 to the minus 9 newtons. Yep. We'll deal with that in a second. Okay. Good. Okay, I'm going to give you one more. This is just one that I'm going to put up on the board. You don't even need a copy of the question if you don't want. Just do the question, okay? The force of gravity between two objects A and B is going to be 100 newtons. Okay, I want to know what that force becomes if we double mass 1, we triple mass 2, and reduce the distance, the separation distance, to 1/2 of what it was. Okay, what does the new force become? Okay, let's see if we can do that. We'll give you about a minute and a half and see if you can get the answer to that, okay? All right, let's finish this one off here now, okay? My equation, my relevant equation, of course, is Gm1 M2 over R squared. If we're talking about the force of gravity, that's always going to be my equation. My original value is that equation, and my original value is equal to 100 newtons. That's what I started off as. That's what my force is before I do anything to it, before I make any changes. My new force after I make my changes, well, G doesn't change, right? It always stays the same, 6.67. But M1 does. M1 is doubled, so it becomes 2M1. Mass 2 is tripled, so it becomes 3M2. And the distance that separates them is cut in half. So instead of being R, it's 1/2 of R. And we can't forget to square everything. Not just the R, but the 1/2 as well. So let's put some brackets in there. Let's pull the numbers out in front. I end up getting 2 times 3 over, what number do I pull out for the bottom? What is it? Yeah, it's a quarter. It's 0.25. And the reason it's a quarter, not a half, is because a half squared is a quarter. I got to pull that number outside of the brackets and out in front. So now we're left with GM1M2 on the top and R squared on the bottom. We know what its value is. It's 100 newtons. So we're going to say 2 times 3 is 6. 6 over a quarter is 24. 24 times 100 is 2400. A lot of people showed me what they got as I was walking around here, and a lot of people got 2400. How many people did get that? Good. Good. A little bit of a tricky concept here that you guys have seen this morning, and you guys seem to be doing okay with it here at this point. Okay. We're still going to do a force problem, a force of gravity problem. We haven't moved beyond that yet, but this one's going to be a little bit different still. This one says, during a lunar eclipse, the Earth, the Moon, and the Sun are aligned in the same plane as shown in 4.19. We want to find the force exerted by both the Moon and the Sun on the Earth. So the Earth's in the middle. The Moon pulls the Earth to the left. The Sun pulls the Earth to the right. What's the net force going to be? The total force going to be? The Moon pulls the Earth to the left. We're going to call that FME, the force of the Moon on the Earth. And the Sun pulls the Earth to the right. We're going to call that FSE, the force of the Sun on the Earth. It doesn't really matter what you call it, right? I'm choosing to call it FME and FSE, the Moon on the Earth, the Sun on the Earth. You can call it F1 and F2 if you want. Let's get the values of both of those forces. The force of M on E, the Moon on the Earth, is GM M Moon, M Earth over R squared. We've got the numbers. We've got the numbers for both of those. The mass of the Moon is 7.35 times 10 to the 22. The mass of the Earth is 5.97 times 10 to the 24. And the distance that separates the Earth and the Moon is 3.84 times 10 to the 8. Don't forget to square that. Okay, let's get that value now. Let's get the value for the force of gravity on the Sun, the Moon on the Earth. 6.67 times 10 to the negative 11 times 7.35. Don't like dealing with all these exponents, but it is what it is. Oops. Okay, that's the top number. Let's divide that by the bottom number. Let's go some brackets here. 3.84 times 10 to the 8. Let's square that. 1.9848 times 10 to the 20. That's a big force, right? But you got to figure, in order to keep the Moon in orbit around the Earth, it's going to take a big force. We done? What do we got to do now?
Figure out the same value for the Sun.
Yeah, let's do the same thing for the Sun on the Earth, exactly. Let's find FSE. Mass of the Sun times the mass of the Earth divided by R squared. So again, the constant is always the same. The mass of the Sun is 1.99 times 10 to the 30. Times the mass of the Earth is 5.97 again. The distance that separates the Sun and the Earth is 1.5 times 10 to the 11 meters. You guys ever watch a show called Who Wants to Be a Millionaire? I don't know, is it even still on TV? Is it? I remember one time this guy was on here, the $1 million question. And I'm like, there's so many, I used to watch that show all the time, but yeah, so I don't even know if it's on anymore, but the $1 million question is, how far away is the Earth from the Sun? And I'm like, I know this. I could win $1 million. I know this. I could be a millionaire right now if I was on this show. The only problem with it would have been that I would have missed the $100 question on the nursery rhyme. It always starts it off, right? I was always brutal at those Those nursery rhyme questions or those kids story questions. Give me the distance between the sun and the earth. I can answer that one. 1.50 times 10 to the 11. Of course, we got to square that. 6.67 times 1.99 times 5.97. Let's get the number on the top. Let's divide it by, use some brackets here. 1.5 times 10 to the 11. Square that. We get 3.5218 times 10 to the 22 newtons. Now what? I get two values of force. We're only looking for one. What am I going to do with them?
You're going to subtract one value by the negative of the value.
Yeah. We're gonna add them together, but when we add them together, we got to make sure this is just like our problems back in Unit 2, right? We got a free body diagram with two forces. F net is equal to the sum of the forces. Let's add them up. F net is equal to F ME plus F SE, which is negative 1.9848 times 10 to the 20 plus positive 3.5218 times 10 to the 22. What do we get for that? .50 times 10 to the 22 newtons. Positive value, so it's to the right. The net force is to the sun, in other words, which we would expect, right? Which exerts more gravity on the Earth, the moon or the sun? Clearly the sun, right? Because we orbit around the sun, not around the Earth. Or sorry, not around the moon. All right, guys. Here's your homework. And you can work on this over the next few minutes in class during scheduled help today. I want you to do page 209, question number 1. If you're looking for a challenge, then you can do 209, question number 2. Although I'm not going to assign that as formal homework. Maybe we'll give some kind of prize for somebody who solves question number 2, though. Okay. In addition, I want you to do the following questions. Page 215, number 1 and 3 to 6. So question number 1 on page 209, and then we've got 5 questions on page 215. And if you're up for a challenge, which you should be up for a challenge, try question number 2 on that page. Okay. I think you can do it. I think you can get question number 2. We'll see.